The analysis of variance, or ANOVA, is one of the most widely used tests in the applied biosciences, and therefore it's a good one to include in our range of testing today. We're going to look at the most simple version, the one-way analysis of variance, which is basically you take three groups and you compare them for a particular measurement of interest. In this exercise 1 with the cattle data, we're looking at 3 different vaccines and whether they've affected the weight gain in kilograms per week of these animals. So here, just to demonstrate, I've got the data in rows. So here we've got vaccine A, and here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 cattle. Then we have 8 cattle on B vaccine, and we have 10 on C vaccine. And for this test, it doesn't matter that we've got equal groups as long as we've got sufficient numbers and replicates in each treatment. For our statistical analysis, we're going to use Jamovi. And for Jamovi, we can't have the data in this format. We need to have it in columns instead of rows, first of all. So there's a nice command in Excel. If I select all of the data, including these blank ones, and I copy that, it's got to be copy, you can't cut it. And then if I right click, I have these different paste options. This one gives me the same again. This one would give me just the values and no extra detail. This would just do the formulas if there were any. But this one with the arrows is transpose, and that's the one we want. And you can see that it's put it into columns. But that's not enough yet. You'll see that I have this in colour down the bottom, so I'm just going to delete that. You see here we've got these 3 columns for A, B and C, but what we need for the analysis is we need the grouping factor, the vaccines to be in one column and the weights to be in the other column. So what I've done is I've essentially stacked these outcome variables, the weights, underneath each other. You can see the orange, green and blue, and then I've put the actual vaccine A for the first 8, B for that, sorry, 9 and 8, and then 10 underneath. For Jamovi, remember I can't copy and paste the column names directly. I can either copy them as a memory to help me put those things in, but I'm just going to do it the easy way. I'm going to copy the numbers and factors only. So right click, copy, go to Jamovi, and I'm just going to paste them in here. So right click and paste. And I think I can remember that if I double click the top one, I can call this vaccine. I think it's vaccines in the actual example, so I'm going to have vaccines, and that is nominal data, names, and here you can see the levels here if I wanted them, and it's text. And then I go on to the next column. I can double click B, or I can move over here, and B, well, that's the weights. So I'm going to put that there, and that's continuous data and decimal, so that's correct too. Okay, so I can move up from there. ANOVA is right in front of us, look. So we're here, we click on the ANOVA, and we've got a number of choices. Well, we're going to go for the simplest version, which is the one-way ANOVA. This second one, the ANOVA, also does a one-way ANOVA with a lot more options to it, but we're quite happy with this one. So we're going to go for a one-way ANOVA. And it brings up a table ready to go. So here's our ANOVA table ready to go, and we just need to put the data in. So dependent variables, that's what we measure. That's what's dependent on our other grouping factor. So we're going to put vaccine there by clicking vaccine and moving it across with the arrow. Oh, sorry, weights and moving across with the arrow. And then vaccines is obviously the grouping variable, so I'm going to move that there. There we go. So we've got weights and vaccines, and here it's done the analysis of variance. Now, by default, the analysis of variance uses the Welch's ANOVA, which is actually a fairly recent addition to the canon. And for the Welch's ANOVA is quite clever in that it doesn't require the equal variance in the different treatments. The traditional one was the Fisher's exact test, so the Fisher's version of the analysis of variance, and that did require equal variance, and any departure from that equal variance caused quite major difficulties in the interpretation. However, for this, I'm going to use both because the fishes one is what most people are taught in class. So I'm going to put them both and you can see them side by side. You can see that fishes gives you the traditional degrees of freedom. So there's 3 treatments, so there's 2 degrees of freedom here. There's 25 cattle. Is it 25 cattle? 8 plus 9 plus 10. Yes, so there's 20 8 plus 9 plus 10 gives me 27 here, and then there's 2 degrees of freedom here, and then 1 more has gone, leaving us 24 residual degrees of freedom here. So then we've got the slightly different probability value for the analysis of variance. Actually, the Welch's one comes out as demonstrating slightly more chance of probability of there being a difference with this lower p-value, and that's because of the adjustment based on variance. But we can look at that. So here, let's have a look at the descriptives table. That will give us our means and our standard deviations and standard errors. So here we've got A, B and C, and we've got the mean is clearly highest for vaccine A, so they're growing fastest, and then lower for B and lower for C, and there's our associated variations with that. If we looked at the standard deviation, which is giving us the variation around the mean for each of the vaccine groups, we can see that it is slightly different. And we can actually do a proper test. It's called a Levene's test. If we put a tick in the homogeneity test box, we can do that Levene's test, and we can see that although these variances, so standard deviation is the square root of the variance, but you can see that these are different because the p-value is not approaching significance. It's not something that we're overly concerned with, although the Welch's ANOVA is increasingly used in science because you don't need to be concerned about these things. Another assumption is normality. If we've got a small sample size like this, normality is particularly important. If we were looking at more and more, if we had larger group sizes, then say 15 in a group, we don't actually have to worry about normality. So departures from normality aren't really a problem for either of the ANOVAs. But here, with the larger group sizes, but with the small group sizes, they really are. So here we do run a Shapiro-Wilk test. If this is significant, then we are going to be concerned about violating the assumption of normality and any consequences for that. But here, because it's a long way from significance would be 0.05, and here we're 0.64, 64% chance that there is no departure from normality. And then we're good. And there's basically all of the information we need for the analysis of variance part for this. If we wanted to have a quick look at the plots, it's always worth plotting data. Should have done this first really. We've put a tick in there, and there's our graph quite clearly showing that A is the highest one, and nothing we're going to do is going to change that. I'm going to take the tick out of that box though, because we don't need that. We can do a better presentation using Excel than Jamovi can do with the data presentation. So we've got 3 vaccines, A, B and C, and A, they grow fastest and they grow slowest on vaccine C, but we still don't know. So we know that A is significantly different from C because it's the highest and lowest one, but we don't know the status of B, and that's where the post hoc test comes in. So if we look at the post hoc tests, if we use the more complex version of the ANOVA up here with this one, we can pick from a range of post hoc tests, but here we just get a choice of 2 post hoc tests. Tukey is a very standard one for equal variance, Games Howell for unequal variance. Tukey tests, we're going to put that one in there, and it comes up with this matrix of the ABC groups versus ABC, and here by default it gives us the difference in the means between A and B, so 0.568 is the difference between this mean here for A and this mean here for B, and it's told us that there is no significant difference between the means of A and B. Equally, if we look at A and C, we test the mean difference, but this time the p-value is just significant. So A and C are indeed significant. We know that because the ANOVA is significant overall. So there must be a test. There must be a difference in there somewhere. If we look at the difference between B and C, it's the lowest of the mean differences, and there's no significant difference there either. So A is different from C, but B is the same as A and the same as C. Which is quite complicated, but we'll show you in a moment how we present that in our information. Okay, so these are all the information we need. We're going to then right click, we can copy the analysis, and we can put that back into Excel if we want to. If we use this one, it gives you all the formatting, so we're going to keep the source formatting because it's a bit tidier that way. What we need really are these data here. If I just highlight them, let's highlight them in a nice colour, in the red. Here, these are the data we would use to create any tables or graphs. But they're not really in the right order. Here, we would probably want the groups across the top and the outcome variables down the side. It's likely in an experiment like this that we are not just looking at one particular weight gain, but we're looking at a whole range of dependent variables, and they would normally go down the side with the vaccines across the top. And so if what I've done in your handout is produce this table which shows you to have a full title, its means and standard deviations, and here we've got the 3 vaccines, and here we've got the number of animals in each group, which can be informative too. We've got the means here, and the standard deviation is in the brackets for the average weight gain in kilograms. So we've got it to the correct number of decimal places, which is one more than the measured value for each of these mean and standard deviations. The last thing to look at is how those post hoc test significances were presented. Remember that A and C were different, but A and B and C were the same. Here, what we're saying is that different letters in the same row include a significant difference. So A is different from B. So we give a superscript of A and B for these two. But vaccine B is not different from A. So that gets another A, and it's not different from this group in B. It's almost like we've got two groups here, like a Venn diagram, and only vaccine B is between them both. So here we've got A, AB, and B. And that's a really neat way to present your table. Similarly, if you look at the handout, you'll see that we can do a bar chart with these means and standard deviations, and there's different ways of presenting the post hoc information as well. The one-way analysis of variance, a real workhorse for our bioscience and for our particularly in our land-based studies. Thank you for watching.